This video is for section 8.1 in geometry. We're going to talk about geometric means. So first we got to define what is a geometric mean in a proportion. A is to B as C is to D. C and D, I'll switch colors here, struggling. C and B are called the means. So you remember that when we had, right, A over B equals C over D, right? I'm making those colors again, using those same colors. You remember that B and C are interchangeable, right? Those are going to be called our means. We're just setting up proportions again in this section. Actually, the same kind of proportions as last chapter. It's just a much quicker way of doing it. And we have a new style of problem where maybe B and C are interchangeable, but B and C are also equal to each other. They're the same. And that adds in some new twists. So our first theorem here, we're saying that if the altitude of a right triangle is drawn to the hypotenuse. That was weird. Spelled out right. Then the triangle's formed. Symbol. The triangle's formed are all similar. So we saw that last chapter. So there's a triangle right here. We know that actually this big triangle is similar to both smaller triangles that are formed once that altitude was drawn. So I have three similar triangles, and we can set up proportions based off of that. And that's all this theorem is setting up those proportions, but also recognizing that x is going to be the same in two different triangles, right? And y and z. So your theorem is called Mario theorem. It's not actually called Mario theorem, but this is what the old teacher liked to use because it was really easy for students to remember. It came from me playing Mario when I was a little kid, and so that's a weird story in and of itself. But mom always looked at the screen and saw Mario taking these choices, these paths from one point in the map to the other. And so she was thinking about this theorem and the way you could describe it as, okay, if Mario slides down, right, that side of the red triangle there, that's also a side in the green triangle, right? And from the bottom, Mario has two choices. He could either just take A across to that point in the hypotenuse where the altitude meets, or Mario could go all the way across C, and again, A and X are part of the small triangle, that green triangle. X and C are part of the bigger triangle. And the way you would set up that proportion is you'd have, let me see if I can color coordinate this correctly. You could have A is to X, right, from the green triangle, as X is to C in the red triangle. But notice that that puts X in my means position. And X is the same value in both triangles, So a lot of times when we're solving for x, we have x squared equals a times c, and when you have actual numbers, you can solve for these things. But essentially, we need to know that there are three different proportions that could be made. You can have that one that I just drew with x's in it. You could have one with y's in it. So the y one would be dealing with the two smaller triangles, right? So it's, what would it be? B over y equals y. Let me switch colors. This is getting a little distracting for me, but that's okay. Y over a, right? If Mario goes down the center, if he goes down y to the hypotenuse, he could either travel along a to one end or b to the other end. The choices at the bottom are your two extremes, a and b, and your means are the y. So that means I can set up that z proportion as well. That's going to be with the red and orange triangles, right? And it doesn't really matter. You can put the z's here, and that's going to be orange for the other one. They could be in that part of your proportion if you wanted to, because it's not going to matter, right? But the other two factors are automatically those choices at the bottom. So if I traveled down z, I could either travel across b midway across the hypotenuse, or I could take c all the way across. So my b option technically would go with the orange z, and my c option is with the red. But doesn't really matter which one's where because z is congruent to itself. So I can flip-flop pieces, I can flip this whole proportion over, but it's just a really quick way to set up the same proportions that we had last chapter. So you'll see what I mean in examples here as we do them. So if I come up to the top over here, all I'm going to do is I know that I'm going to have x in my means or extremes position. Doesn't really matter which one you think about. But at the bottom, if I travel down x, I have two options. I can go part of the way or all the way across, and that's going to be 3 or 10 for my setup. So then I have x squared equals 30, and I just solve, right? And that's where the simplifying square roots comes into play, because that's what you get a lot of times. So 30 doesn't clean up very well, so x is just root 30. And y, I do a similar thing. Y over 3 equals 7 over y, because 3 and 7 were my two options. I go down to the middle, and I can go left or I can go right. So y squared equals 21. Square root both sides, and you get an answer. 21 also doesn't factor out very nicely because 3 and 7 are both primes. So y is just root 21. But some of these clean up better than others. This just happens to not. And then z, right? If I go down z, and again, I can put z in those original means positions and then put the 7 and 10 here. Doesn't really matter because you can flip-flop things, right? I could have put the 10 top left and 7 bottom right. I'm still going to get the same thing because when I cross multiply it, z squared equals 70. Again, 7, 2, and 5, I can't really break that 70 down very much, so z actually is just root 70. But again, some things clean up better than others. So on my next example here, 6 happens to be given to me, and it's going to be my mean, right? So when I set up that first proportion with x, x actually isn't my mean. It's one of the options in my paths at the bottom. So I can go down this side, I can go part of the way, I can go all the way across. So I have two 6's that are the same, and then I have an x versus an 18. So this is a different kind of problem, right? This one can be solved differently. 18x equals 36. X would be 2, because I just divide the 18 across. Once I know that x is 2, then I also know what w is, because w's got to be 16, so that 2 and 16 add up to 18, right? So whether I write anywhere that w equals 16 or not, I already indicated that in my diagram. But now I can solve for y, because y is to 2 as it is to 16. They're just reversed. flipped proportions, remember y is in the same position it is in the means position, and I do that same thing I did before, y squared is going to be equal to 2 times 16. Now I don't actually multiply those things out because I know I'm just going to square root the whole thing anyway, and it's easier for me to see, oh, 16 is a perfect square, so y equals 4 root 2. Fast and easy, right? So sometimes I don't multiply things out because I don't want to. It'll make it easier for me not to. But otherwise, z. And as you get better and better at this, you start to recognize that, oh, all I'm going to end up getting is a z squared equals, what is it, 16 times 18? So whether you even set up the proportion or not, you can do the z's in your extremes positions or not do it. Whether you set up this proportion or not, with your z, with your z here and here, and a 16 here and 18 here, if you can figure out what your equation needs to look like, you're going to be able to get the right answer. So it doesn't really matter how you do it. From here, again, 16 is a perfect square, and 18 I'm going to have to break down into a 2 and a 9, 9 being a perfect square. So z should be 3 times 4, it should be 12 root 2. But now we got our answers, we're good on that one. So this last triangle down here, just to run through it very quickly, right? Again, I already know that x is going to be in two places, so I'm going to have an x squared equals 16 times the whole distance. W is going to be 25, so I have to, figure out w first, but not terribly difficult. Now when I do square roots, that's a 4 times 5. X is obviously 20, right? So then I do my y, and so y squared equals, I could go this way or this way at the bottom, so it's going to be 9 times 16, both of which are perfect squares. So when I square root both sides, y equals 3 times 4, it's going to be 12, right? And then finally I do my z, right? Same thing. I know it's going to end up being z squared. I know my two paths are 9 and the whole distance, which is 25, right? So 9 times 25, square root those, z equals 3 times 5, which is a 15. So hopefully that explains how to set up your problems for Mario Theorem. But otherwise, just do what you need to do. But this is supposed to help you remember how to set things up easily. So that's good enough for these notes.